Welcome. Today we are going to be talking about section 11.2, which is on vectors in 3 dimensions. And to get us started, we kind of need to start out by thinking a little bit about 3-dimensional space, which is not something that we've done a lot of in Calculus 1 and Calculus 2. So in Calculus 1 and Calculus 2, we have an x and a y direction, but typically we are not dealing yet with a third direction, and we're going to call that z. So let me draw a plane here, but I'm going to draw it a little differently than I normally would. I'm going to kind of draw the x-axis, and now we're going to kind of think of the positive x-axis as going down, and then the positive y-axis as going to the right. And then if those are the x and the y-axis, and you can kind of think of the markings here and the markings here, so that you got points out here in the plane. And then we could draw our z-axis, which is going straight up from there. And so here's our 3 dimensions. And so if you were looking at a point like 1, 1, 3, and then you could think about that going over 1 in the x direction to get here, 1 in the y direction to get here, and then 3, 1, 2, 3 in the z direction. 3 in the z direction, and for some reason I'm just lost my color. Three in the z direction, and we get our point right here, which is 1, 1, 3. Okay, so just the same as the xy plane, we're just adding a third direction. One thing of note, though, is that I have my x pointing down and my y is pointing to the right. And the y could be just as easily pointing to the left, and we would just describe the system differently. So the way that we look at this, we call this a right-handed axis system. And why we call this right-handed is if I point, if I had my hand on this axis sitting on top of it, and my thumb was pointing upward, so I am going to just really quick try to do something semi-artistic. We'll see if it is a failure or not. But if I have a thumb pointed upward and my fingers are pointed this direction, and this is the palm of my hand, then if I curl my fingers at this point, the palm of the hand is facing us. If I put your hand out and kind of imagine your thumb is pointing up in the z direction, up this way, and if you curl your fingers, what you'll see is that they curl from x to y. If you curl your fingers, you're curling them starting in the x direction, curling them towards the y direction. And so we call that a right-handed axis system. If the y direction were pointed left instead of right, then you could do the same thing with your left hand, and you would get what's called a left-handed axis system. In this class, in general, we will be talking about right-handed axis systems. Okay, so let's talk a little bit about planes. So in the plane, remember in like the XY plane, so if I put an X and a Y, here's our just normal XY plane, I could write something like the following. I could write x equals 0 as a line. Well, x equals 0 as a line is the y-axis. It is the y-axis. And y equals 0 as a line is the x-axis. So if I write something like x equals 2, then I come over here 2, and I get this nice vertical line at x equals 2, or I could say y equals 1. So I go up 1 in the y direction, and I get this nice horizontal line in the y direction. Well, something similar in 3 dimensions. I can talk about the surface x equals 0, y equals 0, or z equals 0, but all of those things are 2-dimensional planes. So think of it this way. What if I looked at in 3 dimensions, let's look at the plane z is equal to 1. Okay, so first let's draw our XYZ axis. So X we're typically going to draw coming kind of out this way. Y goes to the right. Z goes upward. And now I'm talking about Z equals 1. So if I go up 1 in the Z direction, then I could think about a plane that comes, here's kind of like to a plane that's 1 above the XY plane in this case. So it goes through this point where Z, you're up 1 in the Z direction, and then you have a plane sitting there. So then you could kind of, if you wanted to kind of shade that in, you could, and understand that that's 1 above. It goes through this point 0, 0, 1. Okay. You could also talk about something like y equals 2 as a plane. So let's draw that one. So here's our z-axis. Here's our x-axis. Here's our y-axis. And y equals 2, I'm going to go out 2 in the y direction. And I'm going to put a point because the plane is definitely going to go through that point. And then I'm going to draw kind of a line in the x direction and a line in the y direction. And I know it goes through those two. So now I could draw and we see that plane sitting right there. So if we wanted to shade it a little, we could. Okay. I think one of the more challenging pieces of taking a class in like Calculus 3 is just starting to be able to visualize things in 3 dimensions, where it's much harder than in 2 dimensions where you can just draw it on the board and it's exactly right. It is 2-dimensional. When you start drawing 3-dimensional things on a board, you have to use your imagination a little bit, and that can be challenging at times. So that's something you'll have to practice as you go through this course. It's just your ability to visualize something in multiple dimensions. So let's do an example or two and just see what something looks like. So let's take an example. What would the equation slash inequality z is greater than or equal to 0 look like in 3 dimensions, or if you prefer, in space. Okay, so what does z is greater than or equal to 0 look like in space? Well, let's draw our axis system. We've got x, y, and z. And z equals 0 is the xy plane. So if I continued on the y-axis and the x-axis, we can kind of see we've got the xy plane sitting right here. And if I said that z is greater than or equal to 0, so it is that plane, and it's everything above that plane. So plus everything above that plane. So everything up above the plane as well is included. So include the xy plane, which is sitting right here, and then everything above it. So you can kind of visualize this is like half of space that we're talking about here. Okay? Let's do one more of these. So what would -1 is less than or equal to y is less than or equal to 1. What would that look like in space? Okay, so again, let's draw our 3-dimensional coordinate system. Here's x, y, and z. And now I want to draw the plane y equals 1. So y equals 1, I come up 1, and then I'm going to draw in lines that are parallel to the x and the z-axis, complete those lines, and then I can think of the plane that goes through those lines. And then you've got the plane y is equal to -1. So if y-axis comes out here, I go back 1, and then I'll do the same thing, draw some parallel lines to the x and the z-axis. And then here's another plane. And then I want everything in between that. So y is in between those two planes. So all the space in between those two planes is what we're talking about here. So I've got kind of this slice between -1 and 1 of space that goes on infinitely in all directions, x and z. Okay. Now, what if you wanted to graph something in 3 dimensions? So, similar to graphing something in 2 dimensions, but it gets a little bit more complicated just when you're trying to view it in 3D. So let's try one. So, an example, let's say we wanted to graph x squared plus y squared equals 4, and z is equal to 3. All right, so let's take a look at this and see what we can do with it. So we kind of recognize this guy. This is a circle of radius 2 in the xy plane. But they tell us that also z equals 3. So when I draw my 3-dimensional axes, let's go ahead and keep labeling it because we're not as familiar with these 3-dimensional axes yet. So I've got x squared plus y squared equals 4. And what I'm going to do is I'm going to start out, let's just draw that in the regular xy plane. That's not so good. let's see. So I get kind of a circle in the xy plane that goes out 2 in each of these directions. And then that, if I didn't have this additional z equals 3, if I didn't have this additional equation over here, then this would just be an infinite cylinder going up and down in both directions here, where every cross section of this thing would be a circle of radius 2. But what this is saying is, okay, but I have an additional condition that z is 3. So if I go up 3, 1, 2, 3 in the z direction, then I get a plane. Z equals 3 is a plane. So that plane looks something like this. And it intersects with that infinite cylinder on some circle. And that circle is the intersection of this infinite cylinder and this two-dimensional plane. So intersecting this cylinder that goes on infinitely far with this plane gives me this nice circle that's raised 3 above the xy plane. Okay, so intersecting those two equations gives me this circle. And you get the idea. Okay, very good. Let's talk a minute about how do we calculate distance between points that are in space. All right, so if we're taking the distance between points in space, we already talked about last time how do we take distance between points in the plane, and it's actually very similar. The distance between points in space is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So you could kind of say that this comes from like a Pythagorean theorem in 3 dimensions, so to speak, and that's exactly true, actually. So you notice that if I don't look at the z piece and just have the x's and the y's, that's exactly from the Pythagorean theorem. We're just adding in a 3rd dimension, and so we get this z sub 2 minus z sub 1 squared. Okay, so let's do a quick example here. Let's find the distance between the 2 points, first 1, 0, 3, and the point 0, 2, 2. All right, so if we want to find the distance between these 2 points, let's call this our point number 1. This will be point number 2. And so the distance between those 2 points is the square root of x2 minus x1. So here's x2, here's x1. I get 0 minus 1 squared plus, then I have y2, y1. 2 minus 0 squared, and then I get z2 minus z1, which is 2 minus 3 squared. All right, what is that? I get square root of, this is 1 squared, which is 1, plus 2 squared, which is 4, plus negative 1 squared, which is 1. And so I get the square root of 6. So there's nothing really that different about finding distance between 2 points in space as there is finding distance between 2 points in the plane. You do the exact same thing, just with another variable thrown in there. Okay. So something that we deal a lot with in 3 dimensions. Just like we deal with a circle a lot in the plane, we deal with a sphere a lot in space. So we should probably talk about the equation of a sphere. And it's basically exactly what you might think. So the standard equation of the sphere of radius little a and center x sub 0, y sub 0, z sub 0 is the following. So you take x minus x0 squared plus y minus y0 squared plus z minus z0 squared is equal to a squared, where a is the radius of the sphere. Now notice, if you just again erase the z part of this thing, then you just get the equation of a circle in 2 dimensions. So adding back in that z component here, you just move this into 3 dimensions and you get our 3-dimensional sphere. So now we could manipulate things a little bit and maybe use this to help us better understand an equation. Let's do an example here. So example, find the center and the radius of the sphere x squared plus y squared plus z squared plus 4x minus 4z is equal to 0. Now, this sphere is not in standard form currently, and we'd like to put it in standard form so that we can easily just read off what the center and the radius are. And to do this, we need to remember something called completing the square. All right, let's do it. So what I'm going to do is I'm going to group the x terms together. So I've got an x squared plus 4x. I've got a y squared, which is all by itself. And I've got a z squared minus 4z, all equal to 0. So now I'm going to complete the square for each of these terms. So I've got x squared plus 4x. And then to complete the square on x squared plus 4x, I take whatever term is by the x, divide it by 2, and square it. So 4 divided by 2 is 2, and then when I square 2, I add 4. And I do that so that this turns into exactly a perfect square. Plus y squared. Y squared is already a perfect square. It's y squared. So I don't need to do anything there. And then finally I have z squared minus 4z, and then I need to complete the square here. So I take negative 4, divide it by 2, which is negative 2, square negative 2, I add 4. And now I need to remember that I didn't just leave things alone. I actually did add to the left side of the equation, so I also need to add to the right side of the equation. So what did I add to the left side of the equation? I added a 4, and I added a 4. So that means what do I need to add to the right side? A 4 and a 4. Okay, so now I'm ready to complete the square. I get x plus 2, quantity squared, if you factor that first parentheses, plus y squared, plus z minus 2, quantity squared is equal to 8. Very good. And now this is a sphere in standard form. So now I'm ready to just read off what's the center and what's the radius. So the center is equal to the point. Well, it's the negative of this minus 2. Here it's really y minus 0 squared, so 0. And here I've got z minus 2, so the negative of minus 2 is 2. So that's my center point. And then the radius is going to be the square root of what's over here on the right side. So my radius is going to be the square root of 8. So after completing the square here, I've got my center and I've got my radius. All right. So the last thing that I want to say is, in the last section I talked to you a little bit about vectors, okay? And vectors can also be described in terms of 3 dimensions just as easily as they can in terms of 2 dimensions. We just add a component. So if I have a vector u, which is equal to like 1, 2, 3, and I have a vector v, which is equal to 0, 3, 7, then I can talk about u plus v just like I did in 2 dimensions. It's just I add each component. So I just get 1 plus 0, 2 plus 3, 3 plus 7, which of course is just 1, 5, 10. And all of the nice operations that we talked about in 2 dimensions in the last section apply perfectly in 3 dimensions. All the operations stay the same, scalar multiples are the same, it's all the same. So now we can start talking about vector operations in 3 dimensions, and we know what we're talking about. It all just works in a similar way. So if I talked about 3u, then that's just 3 times 1, 2, 3. And we know that we can multiply that scalar through the vector and just turn this into the vector 3, 6, 9. So all of the operations that we talked about last time for vectors in 2 dimensions apply exactly the same in 3 dimensions. I think you're ready to do some homework over 3 dimensions, and I will talk to you soon.